Okay, so now if we consider the whole cycle, okay, for the whole cycle we have only an input at the combustion chamber. So Q dot N is just equal to m dot of gas times H3 prime minus H2 prime. Okay. While if we consider the output, okay, of the whole cycle, we have an output at the gas turbine level and an output for the turbine in the steam cycle. Okay, and of course, whenever we compute W dot net, we should subtract the work done at the compressor level here and the work done at the pump level here. Okay, so we should consider then W dot net total. W dot net total is equal, first, from the gas cycle, you have m dot gas times for the turbine, as we said, so it's H3 prime minus H4 prime, and we subtract the compressor, so minus H2 prime minus minus, so plus H1 prime. So this is the net work for that we get from the first cycle. And now for the other cycle, we should add plus m dot steam, okay, plus m dot steam times, so for the turbine, it's H3 minus H4. And for the compressor, for the pump, so you know, for gas, we use a compressor to increase the pressure. For a liquid, we use a pump. That's why in gas cycle, we use a compressor, and in steam cycle, we use a pump. So H3 minus H4 minus H2 plus H1, okay? So now you need to find the overall efficiency. To calculate the overall efficiency of your cycle, you just have to divide W dot net by Q dot N, okay? So here, if you want, when you do the division, you don't know the mass flow rate of each cycle, but you know the ratio. So you can say that Q dot N over M dot gas, okay, is equal to H3 prime minus H2 prime. And W dot net over m dot gas, so per unit mass flow rate of gas, is equal to, here m dot will cancel out, and here you will have m dot steam over m dot gas. And we have already evaluated in the first question what is the ratio of the mass flow rate of steam to the mass flow rate of gas. This is y. This is the fraction y, which was 0.131. Okay? So once you do this, you have y from previous step. You calculated all enthalpies. You can just divide W dot net over m dot by Q dot net over Q dot N over m dot, and you find the overall efficiency. So just to recap, let us see in numbers and compare the efficiency of each cycle alone and the combined cycle. So first, as we said, the first step is to apply the energy balance for the heat exchanger, which is E dot N equal E dot out, okay? So what is lost by gas is, or it's equivalent to what is lost by gas is gained by steam. Now a small remark, in case they give you the percentage of loss, and for example, if the heat exchanger is not perfect, you have 10% losses. Okay, so let's say an efficiency of 90%, 10% is lost to the surrounding. So then you can say that the amount of heat delivered by gas will not be entirely absorbed by steam. A part will be lost to the surrounding. So if I tell you the loss is 10%, then the efficient part is 90%. So just you say that the energy extracted by steam will be m dot gas times h prime 4 minus h prime 5 times the efficiency, or 1 minus the loss fraction. So if I tell you you have 10% loss, you do 100% minus 10%, so it's 90%. Okay, so if you know the amount of loss, you can deduce what is the percentage extracted by steam, because you know you don't have at the end you always have some losses. You'll not have a perfect process. So that's why you can consider efficiencies to find what is the useful amount of heat extracted over the maximum that can be extracted. Okay, so from the energy balance, we got the ratio of m dot steam over m dot gas. And then we are ready to move to next step. So we can say that W net of the whole cycle is W net of the gas cycle plus the fraction Y of W net of steam. Because as we said, if we have 1 kilogram of gas circulating in the 1 kilogram per second of gas circulating in the gas cycle, the corresponding fraction circulating in the steam cycle will be Y, which is 0.131. So that's why to calculate W net, we consider W net gas plus Y times W net steam. And we already demonstrated this together. When you divide by m dot gas, you will have W dot net over m dot gas equal to W net gas plus Y times W net steam. So now, to be able to evaluate W net, as we said, we should calculate all enthalpies. So here, they considered now each cycle separately. And from doing analysis of each cycle separately, as we did at the beginning of the problem, we can get all properties needed, the different enthalpies needed, and using isentropic efficiencies. So as we mentioned, for example, you can calculate first W ideal for the compressor, W isentropic. And you say, because we have some losses, we need to supply more energy. So W compressor real is W isentropic over the efficiency, which is 0.8. And this is what we did, because what is W compressor real? We said it's H2 prime minus H1 prime, okay? While W ideal is equal to H2 prime S minus H1 prime. So by using the isentropic efficiency, we can calculate what is the real work that should be supplied in kilojoule per kilogram at the compressor. While for the turbine, as we mentioned, we do it in the opposite way. We calculate the isentropic work, and we say because of losses, the actual work produced by the turbine will be lower. So we multiply it by the percentage, which is 85%. We get W net in kilojoule per, we get W turbine in kilojoule per kilogram. Okay, and now after getting this information and finding the enthalpies needed, we can evaluate for this cycle alone what is the efficiency. So as we did together, we find W net, which is W turbine minus W compressor, actual, and we evaluate the heat input at the boiler per unit in kilojoule per kilogram. So here we just divide by m dot. So m dot will be simplified at the end. We get the thermal efficiency, and as expected, for the gas cycle, the efficiencies are relatively small because we discussed that we have high amount of losses through the exhaust gases. So to increase this efficiency, we combine the gas cycle to the steam cycle. Okay, so as we mentioned, we can do this by passing the hot gases through a heat exchanger to provide energy to the Rankine system. Okay, so if we do the analysis of Rankine cycle separate without considering the gas system, we get an efficiency of 40% nearly. okay? So you can verify that if you consider steam cycle alone, which is the conventional Rankine, you get a thermal efficiency of 40.8%. Now, let us combine both. So when we combine both, we can find W net for the two cycles. So as we mentioned, we should add W net gas plus Y times W net steam as we derived together. And then we should divide it just by Q dot N for the gas cycle, because we said there is no boiler for the steam Rankine cycle, since heat is completely supplied by the hot gases that are a free resource that we use by using waste heat to drive a new cycle. Okay, that's why in Qn you don't consider, you just consider Qn of your gas cycle, because we consider that exhaust gases are waste heat. So if we benefit from them, it's a free source. We don't have to pay for it. That's why we expect that the efficiency will be considerably larger, because we were able to increase W net while keeping Qn of the gas system the same. Okay, so if you evaluate the thermal efficiency, it's 48.7%. So you can see the high improvement. For the gas cycle, you increase the efficiency from 20, it was around 26.6 to 48.7. And for the Rankine, it was 40.8 and now it's 48.7. So the combined cycle has an efficiency larger than each cycle separately, and we have a considerable enhancement in the efficiency, especially if we take the compared to Brayton cycle alone. So from here, we understand the importance of heat recovery, which is the use of waste energy in order to drive a cycle, in order to, let's say, you can use it for, here we used it for electricity production, because it's driving a Rankine cycle producing electricity. You can use it maybe for domestic hot water needs or for district heating. Okay, so you can, for this heat exchanger, it can be of different types. You can use it in a cogeneration power plant. So we said whenever we say cogeneration, this means that the purpose is not only to produce electricity, to produce several forms of useful energy. So here we say, for example, another application is to have a heat exchanger, okay? But instead of using the extracted heat to operate a steam cycle for which the purpose is to produce more electricity, you say maybe the electricity amount produced is enough, but I need to use this energy to heat water. So I can pass in this heat exchanger water, and I can heat it from a certain temperature, T inlet, to a much larger temperature at the outlet. So depending on what I need, I can determine what is the mass flow rate of water, because you know the amount of energy extracted, let's say, by water will depend. If it will remain in the liquid phase, you can say that it's equal to m dot Cp delta T. And in case it's changing phase, so you need to consider, they need to give you information to know the enthalpies at the inlet and at the outlet state. So we can use several combinations of systems depending on the purpose. If the purpose is to do cogeneration, we can use it then with a heat exchanger to heat water or to heat any other fluid. If we need to enhance the efficiency and to produce more electricity, we can combine gas and steam cycles as we did here. Now, a final remark, when you want to plot the TS diagram for both cycles on the same graph, all you have to do is first to get your temperatures, because once you get your temperatures, you will know the relative positions of the two graphs, okay? So for Rankine cycle, it's very simple. As usual, you have two pressure lines, and you have a dome because you have change in phase, since you have steam that can go from liquid to vapor. So just you need to know the limiting pressures. So here, of course, I will tell you what is the low pressure, what is the high pressure, You know that in general 3 is superheated state, and they will give you the the corresponding temperature. Sorry. And then you have through your turbine. Here for the steam turbine, it's isentropic, so S is constant. And for your condenser, as usual, you exit at liquid state. Okay, so this is how you can draw your Rankine cycle, and you need to determine temperatures. Okay, so you know the temperatures at your different points. You can consider a scale for temperature. Now, for the Brighton cycle, what is different is that you don't have a dome because you have a gas here, you have air, so no change in phase. Okay, and as we mentioned, this cycle operates between two levels of pressure. So you have a line of pressure, of constant pressure here for P high, which is after the compressor. Okay, and you have a low pressure zone that you can reach at the exhaust of the turbine. Okay, and for always for Brighton cycle, the pressure at inlet of compressor is equal to the pressure at exhaust of turbine, and the pressure at exhaust of compressor is equal to the pressure at inlet of turbine. So you can see here that point 2 prime and 3 prime are on the same pressure line, while points 1 prime, 4 prime, and 5 prime will be also on the same line. So if you do extension for the line here, why it's not continuous line? Because it's an open cycle. Okay, so you don't join 5 prime to 1 prime because it's open. Here you introduce fresh air. Here you exhaust gases. So you have CO2, CO, etc. Okay, but as constitution, you can assume that the constitution is same as air. So for simplification purposes, okay? So here, these 3 points, if you complete the dashed line, will be on the same pressure line. So all you have to do to be able to draw your cycle here is to know temperatures. You know at point 1 prime what is the temperature? It's 300. You know that at the exhaust of your heat exchanger, they gave you 5 prime. And these temperatures will allow you to locate these points relative to your other points. Yani from Rankine, for example, point 3 is 500 degrees. So point 3 is above point 5 prime. Okay. And then for 3 prime, it's 1,300. And from analysis of the graph, we were able to find T4 prime. So you can know where this point is. Okay. And once you locate your points, you just have to say that I have a line of constant pressure between 2 prime and 3 prime. And since I don't have an ideal process, it's not straightforward. I just have a small increase in the entropy S. And then I move downward with a constant pressure line, and it's limited by the exhaust temperature, which is 450. While for the compressor, since it's not an isentropic process, it's not vertical, it's a little bit inclined. So this is how I can draw my figure. Okay. Any question on this? Okay, good luck for the exam. And if you have any question, as usual, don't you can contact me anytime. Thank you.